In the last class, we were analyzing when it is not possible to perform pack learning, right? So we initially saw that all finite hypothesis classes are pack learnable, and in fact, they're also agnostic pack learnable. But then that raises the question as to whether all hypothesis classes are pack learnable, and the answer is no. So to derive a lower bound, we use this no free lunch theorem, which essentially says the following: if we are ever in a scenario where the hypothesis class contains at least, or in other words, the domain contains at least 2m symbols, the size of your domain set is at least 2m, and you have fewer than m samples, which is half of the domain set, and if the hypothesis class is the set of all functions from the domain set to the space to the binary alphabet 0, 1, then no learning algorithm is going to be able to achieve an arbitrarily small epsilon and delta. Right? So in other words, you need at least half of the number of samples has to be at least half of the size of the domain if the hypothesis set is the set of all functions from the domain to 0, 1. This seems like we're not sure how this can be used, but we'll see in a little while how this can be used to tell us what is whether a particular hypothesis class is pack learnable or not. But directly using this, we can show that if X is an infinite set and H is the set of all functions from X to 0, 1, then H is not pack learnable. Right? And the reason is because you take any finite subset of X. Let's suppose that you have 2m symbols in this particular set. The set of all functions from this set to 0, 1 is 2 to the power 2m, right? It's a set of all functions from this finite subset to 0, 1. And for this, you need at least m samples, right? So no matter how many samples you have, you're not going to be able to learn even a subset of the functions in the hypothesis class. Because even if you reduce yourself to a smaller hypothesis class consisting of the set of all functions from a subset to 0, 1, you will still not be able to achieve arbitrarily small epsilon delta error. Which means that no matter how many samples you have, as long as you have a finite number of samples, you will not be able to achieve arbitrarily small epsilon and delta errors. All right. So then that raises the question, is it true that all infinite classes are not pack learnable? And we saw an example that is not the case. So if we are given an infinite hypothesis class, how do we say whether this is pack learnable or not? That's what we are heading towards. And for this, we'll see a series of definitions. And using this, we'll characterize the pack learnability of any hypothesis class using a bunch of different parameters. So first, we'll see what is called the VC dimension, and we'll show that if the VC dimension is a necessary and sufficient condition for a hypothesis class to be pack learnable is that it should have finite VC dimension. And then we'll also characterize it using another property called the Rademacher complexity. Right, so that's going to be the agenda for maybe this class and the next. So let's build up towards that. So again, recall that the setup is the following. We have an infinite domain set X, and our problem is a binary classification problem with the 0, 1 loss. Okay. So for this, in such a setting, given any hypothesis class, I defined the restriction of the hypothesis class to some subset. Let's call this subset X subscript M. And X subscript M is any subset of the domain set with exactly m elements. All right. And then you can look at the restriction of H, the hypothesis class, to this particular set X subscript n. In the extreme case where the hypothesis class is the set of all functions from x to 0, 1, the restriction of H to xm is the set of all functions from xm to 0, 1. So let's just note that down as a fact. So then the restriction of H to any xm is simply the set of all xm to 0, 1. And the restriction of H to this set xm is denoted H subscript xm. What is the size of this? Simply 2 to the power m, right? So now, if you had to learn, if your goal was to learn the hypothesis class, if you want to perform pack learning over H, then a simple and almost straightforward lower bound on the number of samples that you require is m by 2. So no matter what the hypothesis class is, suppose that there is some xm for which this hxm is exactly equal to 2 to the power m, it's a set of all functions, then it's clear from the no free lunch theorem that you need at least m by 2 samples to learn the hypothesis class. Because you need m by 2 samples to learn this restriction itself, you'll definitely need at least m by 2 samples to learn the entire hypothesis class. It may be a good lower bound, it may be a bad lower bound, but nevertheless, it is a valid lower bound. So obviously, then we can think of different restrictions, right? Because if we want a tighter lower bound, we'd want a bigger restriction, and that's essentially that's essentially what defines the VC dimension. So this particular scenario, right, where the restriction is equal to so suppose size of xm equal to m, x, and H is a hypothesis class. If the restriction of the hypothesis class to this particular set xm is the set of all functions from xm to 0, 1, then we say that this particular set xm shatters the hypothesis class H. I'm sorry. We say that H shatters xm. All right. So H when restricted to xm is the set of all functions from xm to 0, 1. No, not necessarily. Not at all. There can be multiple hypothesis classes which shatter a given set. There can be multiple sets which get shattered by H. I don't follow. Correct. Yes. No. What do you mean HXM? So you're given two things, right? The set, the domain set X, and a subset XM, and the hypothesis set H. H is a set of all, is some set of functions from X to 0, 1, right? And you're looking at the restriction of this H to XM. What do you mean disjoint? HXM is derived from H and XM, right? It's the restriction of H to XM. So if you go back to, let's say, the example over here where we have threshold functions. So H is the set of all functions which are equal to 0 if x is greater than some particular number alpha, and it is equal to 1 if as long as x is less than or equal to alpha. So it's a set of all functions which look like a step function, all possible step functions. Not all functions, right? It's the set of all, if you apply H, all these H to that particular subset, you get a set of functions. So for example, if you take xm to be equal to 0, 1, 2, which is a subset of the real line, and you look at, you take every H from this set, and then find out what happens to H of 0, H of 1, H of 2, then in this particular example, you get 4 possible functions, right? So you can think of them as functions, you can think of them as vectors or arrays, right? So all possible distinct vectors or all possible distinct functions that you get, which are derived from this particular H, right? Now, in this case, this is H. The restriction of H to XM is not the set of all functions from XM to 0, 1. So this is an example where it does not shatter the set, right? But maybe let's look at the same hypothesis class. So H does not shatter XM. Can you repeat? Yes.
Set of XM.
Correct. Yes. All right. So let's see another example.
In that case, restriction.
In that case.
In that case, restriction should be set of all.
Yes. So let's take another example where XM just contains two elements. Let's say 2, 3. All right. And look at the restriction of H to this particular set. Is there some function H for which, again, what is HXM? It is the set of all H of 2, comma H of 3 that belongs to the hypothesis class. So is there a function little h that will give me 0, 0? Right? Is there some value of the threshold which gives h of 2 equal to 0 and h of 3 equal to 0? Yeah, anything less than 2 will do, right? As long as alpha is less than 2, h of 2 is equal to 0 and h of 3 is equal to 0. Okay, now can I get, let's say 1, 1? Yes, anything greater than, any threshold greater than 3 is going to give me 1, 1. Right? What about 0, 1? Is it possible? It's not possible, right? Because in this case, if exactly. So what about 1, 0? To take any alpha which is between 2 and 3, I'm going to get. So once again, H does not shatter this particular exit. Let's take one more example. Let's take XM to be equal to just the set, say 3, one element. Is there some particular alpha for which HXM or H of 3 is equal to 0? Yeah. Anything less than 3 is fine, right? Is there something that gives me 1? Yes. Anything greater than 3 is it works. So in this case, it is the set of all functions from XM to 0, 1. So in this case, H shatters this particular XM. Okay. Any questions? Yeah.
What's the importance of defining this notion?
We'll see that in just a little bit. So in the example that we just saw with different thresholds, right? There we saw that subsets, the choice of, yeah.
There is no shattering. Which is abbreviation.
There is, right? So for the particular example that we had, singletons are shattered, and this choice of 3 was arbitrary. I could have chosen any number, and H would shatter any singleton set. But H does not shatter more than singletons.
There is no
I'm sorry?
there is any subset with any
Then it's the reverse. Okay, so the size of the largest set that is shattered by by H, this is called the VC dimension. So given hypothesis class H, so we'll say that D is, or the VC dimension of H is D if following two things happen. H shatters XM for all XM having exactly having at most D elements, and there is some XM which is not shattered by H where this XM has more than D elements. So all subsets of size less than or equal to D are shattered by H, and there's at least one subset of size larger than D which is not shattered by H. So it's the maximal size of a set that is shattered by H. So if you go back to our previous thresholds example, what is the VC dimension of that particular hypothesis class? It's just one, correct? But then again, remember that this hypothesis class was infinite, right? So as we'll see, the VC dimension if the VC dimension is finite, then it is packed learning. And coming back to your question as to why shattering is so important, this notion of shattering immediately gives us a lower bound on the sample complexity of packed learning for this particular hypothesis class, right? So suppose that the VC dimension of H is equal to D. All right. What does it mean? It means that if I look, there's some X subscript D which is shattered by H, right? So when restricted to this particular XM, H subscript XM is the set of all functions, right? So if the VC dimension is equal to D, we know that there is some XD right? So for this particular, when restricted to this particular set, the hypothesis class is a set of all functions. Now if I just apply the no free lunch theorem to this particular set, right? If I want to be able to resolve among functions within this particular set, I need at least m by 2, or in other words d by 2 samples, right? If I have any fewer than d by 2 samples, I'm not going to be able I'm not going to be able to learn just this particular restricted hypothesis class. And if I'm not able to learn this restricted hypothesis class, I can't learn the entire hypothesis class. Yeah.
Don't all of the X stays at X. If the size of the set is 2 power D, then X is stacked in X.
Correct.
So then why have you written there exists some X? Don't all X stays?
All XDs, sure. But for me, I know for sure there's at least some XD. Right?
So in a way, we can say that if there are all possible functions can become like
Correct.
x to 0 to 1, all possible functions are there. In a way,
Correct.
we are not getting any information from the hypothesis class for this particular task. Right?
Correct. So suppose that I saw this. So in other words, if I saw these particular samples, right, then it means that I'm not going to be able to tell you which function it was. I've got no information from this particular set of samples. That's the high level intuition. That is when H shatters, yes. Right? So since this happens for every XD, right, every set of size D, no matter how many, if I see D by 2 samples, I'm never going to get any information about which function from the hypothesis class was chosen. So it means that I need at least D by 2 samples to be able to do pack learning at all. Yeah.
Will have information, but the probability
Correct.
will be lower by some large.
Exactly. I have no information. Essentially, I have no information among when restricted to this particular class. Right? That's what I mean.
Plus 1 over there.
Which one?
The second point. There exists some x d plus 1. But can that be any d greater than f?
If it happens for D plus 1, then it will also happen to D plus 2 or D plus 3 and so on. So D is the largest such that all subsets of size D are shattered by H. All right, any questions? Okay, so let's see a bunch of examples just to be clear. So the first thing that we saw was that if you look at threshold functions, let's say x greater than or equal to alpha, we saw the VC dimension is equal to 1. Right? Now let's see another slightly general example where H is the set of all functions for which takes the value 1 if x is between some alpha and beta and 0 otherwise. Right? Yeah. Why?
Because like you have to kind of because you could like make the interface such that it covers anyone and
Correct.
and when you go to like 3 and
Correct.
especially when you're already like so let's just take for example like 1 to 1.
Sure.
So for 1, 2, and 3, you can't have something like 0, 1, and 2.
0, 1, 0 is in fact possible.
Sorry,
The other way. 1, 0, 1 is not possible. So firstly, we see dimension is greater than or equal to 2, the first point, because you can get, if you take any xm, let's take x1, x2, then h x2, you can get 0, 0, right? You can get 1, 1 just by ensuring that alpha and beta are, alpha is less than x1 and beta is greater than x2. You can get 0, 1 just by taking alpha to be between x1 and x2 and beta to be greater than x2. And you can also get 1, 0 by taking alpha less than x1 and beta to be between x1 and x2.
Take 12 with x1, x1 does not belong to that set. Then what x1's mapping always be fixed.
I'm sorry, can you repeat?
I take x1 and x2.
Correct.
And it does not belong to that set.
What do you mean x1 does not belong to that?
Alpha comma. Then interval.
Okay.
Then x1's output is always going to be fixed to 0.
But here again we're fixing x1, x2, and we're varying alpha and beta. That's what. So you keep varying h for the fixed x1, x2. Maybe I didn't get your point. Right. So in this case, the set is fixed, and you're varying over all functions in this hypothesis class, not the other way around. You're not fixing a h and then changing x1, x2.
Okay.
Alpha and beta are things that you vary.
For the moment we put them like that, would that be expansible to the number? Like even if I had 3 elements, x1, x2, x3.
Okay.
By varying my alpha and beta, I can still map to what was equal binary combination.
That's so again, all you can change are alpha and beta in this case, right? So let's look at the following case. Is it possible to get so can you find alpha beta such that, let's say, h of 0 equal to 1, h of 1 equal to 0, and h of 2 equal to 1? You can't, right? Because if you have two extremes where the function value is equal to 1, it should also be equal to 1 everywhere in between. So in fact, the VC dimension has to be less than or equal, has to be strictly less than 3. Right? Just a second. Yeah? Deterministic way. Here it is.
X belongs to R.
Okay. Okay. It's hard. I'm not saying that finding the VC dimension is an easy task. It could be extremely difficult. Without knowing the VC dimension, it's difficult to say what the sample complexity is. But then again, if you want to show that something is pack learnable, all you have to show is that the VC dimension is finite. Doesn't matter whether you have a tight or a loose upper bound on the VC dimension. That can sometimes be easier to see. And sometimes, for example, if you want to compare the relative complexity of two different hypothesis classes, you need to show that the VC dimension of one is less than the VC dimension of the other. That is sufficient. So we later see another measure of complexity called the Rademacher complexity, which will be even more difficult to compute than the VC dimension. But the advantage will be that there's a more direct connection between the Rademacher complexity and pack learning. Okay, so you can generalize this. You look at the set of all functions of the form if, let's say, x belongs to A1, B1 union A2. So it's a union of k disjoint intervals, right? 0 otherwise. What do you think the VC dimension is going to be? K plus 1. Okay, but prove this form. Okay, so now let's look at two-dimensional setting where x is R2, and you have all possible linear classifiers. So it's the set of all h of x equal, which are given by, this is equal to 1 if A transpose x is greater than or equal to B, and 0 if A transpose x is less than B. The geometrical viewpoint is that you basically draw a line, and everything above that line, or one side of the line, is labeled 1, and everything on the other side of the line is labeled 0. Everything above on one side is labeled 1, everything on the other side is labeled 0. Yeah.
So I think it's
Correct.
we label as 1 and 0, that's that.
Not really, right?
Even in like the previous step for the VC dimension.
Correct. Okay.
You took the complement, so R minus the.
So basically x less than or equal to alpha.
Not that, the union of the k disjoint.
Okay.
So you took the complement of that and goes to 1.
So you mean it's equal to 0 if this
Yeah.
happens and 1
That's what
otherwise?
the dimension.
Doesn't change. The labeling doesn't really matter. So of course it's binary, but what you have to be a little careful about is, so I'm assuming that it's only the set of functions for which h of x is equal to 0 if this happens and 1 if this happens. You're not taking the union of those two sets, only one of them. So then the VC dimension doesn't change.
Not take a binary, we consider it like a 3-class class.
Okay. So then the VC dimension is not the right combinatorial quantity. Right? So that's why we're restricting ourselves to binary classification, 0-1 loss. It's only in this setting that all the statements that I'm going to say are true. There are equivalent notions even for multi-class classification as well as regression, but those notions are different. There's something called the Natarajan dimension, but doesn't matter, we won't look at it. Okay. Great. So now we're looking at the set of all linear classifiers. Let's see. Let's look at all possible subsets of size 1. Is the VC dimension at least 1? Yeah. So every set of size 1 is shattered by H, right? Because you just take the line on one side of 1 or the other side of this particular element, right? X1. Okay, now let's look at X2. So take any 2 points, X1 comma X2.
Any subset of size.
For every subset of size 2. Yes. Suppose this is my X1, this is my X2, right? Now if I wanted to get 0 comma 0, what should happen? Both points should lie on the same side of the plane. So for example, this is one scenario where I can get either 0 0 or 1 1, right? Similarly, if the line splits the 2 points, then I can get either 0 1 or 1 0. Everything to the left is labeled 0, everything to the right is labeled 1, or you just flip. Everything to the left is labeled 0 and everything to the right is labeled 1. Okay, what about 3 points? Let's take. I'm sorry?
3 points are collinear, then we can not always shatter.
Okay.
And the not collinear, then we can always.
Okay. So what is the VC dimension? The VC dimension should be equal to 2. Sorry. Let's take the collinear point again. Look at that. Let's take these 3 points and revisit the point that you mentioned. Are you sure that these cannot be shattered? Why do you think it's not possible to shatter them? Correct. Right. It's not. You can get everything else except perhaps 1 0 1 or 0 1 0.
But dimension is the structure.
What do you mean? Does structure exist? So essentially you can't, if I take 3 collinear points, then I cannot draw a hyperplane for which only one point is on one side, and basically the middle point is on one side of the hyperplane and the other two are on the other side. Correct. Well, I can get 1, 1, 0 and 0, 1, 1, but essentially the midpoint, these two having one labeling and the midpoint having a different labeling is not possible. If it is not collinear, well, it's possible, right? I can draw a line which makes sure that 2 points are on one side, 1 point is on the other side, right? Sorry? Yes. In the collinear case, I can get 0, 0, 0, 0, 0, 1, 1, 0, 0, 1, 1, 1, and 1, 1, 0, and 0, 1, 1. Right? All of these are possible. Okay. Here's something maybe a little more tricky. So suppose that H is the set of all functions x over the reals, which takes the value 1 if, let's say, a0 x plus a1 x square. Let me write it. A0 plus a1x plus a2x square ak x to the power k is greater than or equal to 0 and 0 otherwise. Yeah. There's a k for a fixed k, okay? I'm fixing k. So if you want, just think about set of all quadratic functions. Okay. Just to be concrete, let's fix k equal to 2.
If I know that it's particular,
Okay.
can I then conclude we should have a
We'll see that. Just hold on to that a little bit. Clearly, if the VC dimension is infinite, then it's not path learnable, right? That much is clear. But if the VC dimension is finite, it's still not sure if it is path learnable or not. We haven't seen that. But as we'll see later, if the VC dimension is finite, then it is path learnable. Yeah, and we'll see that the VC dimension, in fact, gives us a bound on the sample complexity. All right, so going back to this example, what do you think the VC dimension of this class is? 3, and why?
We can map, if we have 3 points,
Okay.
we can have a three-dimensional students to order the polynomial subtract some C from it so that if the value is 1, we can have it as any otherwise like it's Lagrange polynomial.
Okay, there's a suppose I wanted to extend this to a general K. What's the intuition?
K plus, if you're going to map like K plus 1 points, you can map with a K value.
Okay, how do you do that?
I don't know how, but yeah.
Okay.
I studied a theorem which says that polynomial.
Okay, I mean, is there a more sort of geometric way of seeing why that's possible?
We're not able.
Okay.
So given 3 points.
Okay.
So if minus a0 minus a1 by a2 is the midpoint of your parabola.
Okay.
And using the C, you can even its height based on whatever set of points you have. So using those 3 parameters, you can shift your parabola around in the space such that you can get all possible combinations, all possible binaries.
Okay. So let's maybe do it step by step. So first, you take any 3 points. Okay. You look at x3 equal to x1, x2, x3. All right. If I give you any 3 points or pairs of points, let's say y1, y2, y3, can I construct a quadratic which passes through x1, y1, x2, y2, x3, y3? Okay, the question is, I give you a triplet, right? x1, y1, x2, y2, x3, y3.
We can always find a parabola path.
Any 3, right? I can always find a parabola that passes through these 3 points, right? So if I wanted to get a particular combination, say 0, 0, 0, 1, 1, 0, all I have to do is either take a positive value of yi or a negative value of yi, depending on whether I want that particular h of xi to be positive or negative, to be equal to 0 or 1, right? So you can kind of see that h shatters any set of 3 points. Okay. What about 4 points? And why not? 1, 0, 1, 0. And why is that not possible?
Let's see, I have a parabola passing through.
Okay.
Consider a 4th point which has the same.
No. So one thing you have to keep in mind. In this case, you know y1, y2, y3. All I am saying is I want positive, negative, positive, negative. So effectively, if you want to say, if you want the restriction to have, let's say 1, 0, 1, 0, all this means is that can I find a polynomial for which at the first point it is, let's say, positive, negative, positive, negative. It doesn't matter which points it passes through, right?
Function's derivative would be 0 at these 3 points.
Derivative equal to 0 is a much more fundamental reason. Okay, why? Yeah, this should have 3 roots, right? Because between a positive and a negative, if it has to change sign, then it must pass through 0, which means that is a root. So if it is changing signs once, twice, thrice, then it must mean that it passes through the x-axis 3 times. It should have 3 roots, which is not possible because it's a quadratic. Right? So in general, therefore, if this were any polynomial of degree k or degree at most k, then what would be the VC dimension? K plus 1, right? So in this case, it's equal to 3 in general. Okay. So at least so far in all of the examples that we've seen, the VC dimension happened to be equal to the number of free parameters that we had in hand, right? So you see in this case, there are 3 parameters. In general, for a polynomial of degree at most k, there are k plus 1 parameters. The VC dimension happened to be k plus 1. In this case, where you had hyperplanes, the VC dimension happened to be equal to 2, although you had 3 parameters. And in this case also, the number of free parameters was equal to 2 and the VC dimension happened to be equal to 2. But that intuition doesn't necessarily carry forward in general. Here is an example. Again, I won't prove this, but I'll leave it as an exercise. So suppose I look at the set of all functions of the following form. Where the polynomial, there are, if you have a polynomial of degree at most k, there are k plus 1 parameters. Correct. So this is a polynomial of degree 2, right? There are 3, right? 1, 2, and 3. No, it's equal to 3, right? So if it's a polynomial of degree k, then the VC dimension is k plus 1. Not because there are k plus 1 free parameters. That's the point I'm trying to make, right? The number of free parameters does not necessarily equate to the VC dimension in general. In this case, yes. This specific case. So in this case, there's only one free parameter, alpha, just the frequency of your sine wave. But as it turns out, the VC dimension of H is infinite. Okay, so let's take one last example. Suppose H is a finite hypothesis class. Then there's no parameter, right? There's only one function, right? There's only one function in the hypothesis class, right? We want a class of functions. So there has to be at least one free parameter. Okay. So let's assume that H is any finite hypothesis class. These are all infinite hypothesis classes, right? So far. That's exactly what I'm coming to. That's the example we have. Okay, so suppose that H is a finite hypothesis class. What is its VC dimension? Equal to the size of the hypothesis class? No. It's an extremely loose upper bound. There's a much better bound in terms of size of H. No, H is fine. X could be infinite. No, definitely no. You mean cardinality plus 1? I'm saying that cardinality of H is an extremely loose upper bound. There's a much better bound. It's much smaller than the cardinality of H. Okay, so firstly, let's go back. What is the definition of the VC bound or of the VC dimension? Means that all sets of size at most D are shattered by H, right? So the restriction to any X sub D is the set of all functions on X sub D, correct? Which must mean how many different functions can you generate over a set of size D? 2 to the power D, right? Which means if I have to get 2 to the power D different functions, then my hypothesis class should have at least 2 to the power D different functions, right? Because the restriction itself should have 2 to the power D different functions. At least 2 to the power D, right? So then what is the VC dimension, or what is an upper bound on the VC dimension of any hypothesis class, finite hypothesis class? Log of the size of H. It could be smaller, but it definitely can't exceed log of the cardinality of H. Not necessarily, right? Depends on how the hypothesis class behaves. Right. Yes.
And we know that the hypothesis is only finite. So we know that there's at least one element in X that can't be back to like 1 and 0. Right, so what I mean is like, so there's at least one element in X. No, there's at least one element in X such that even if you consider all functions in the hypothesis, like,
Okay.
if you take the image of this element, it can't be like 1 and 0, right?
In isolation, it can, right?
So what I'm saying is like, so if there's a possibility for like every element in X to be like either 0 uh, or 1,
Okay.
then how can the hypothesis start?
So right now, I'm not saying that X is infinite, right? So I'm only looking at the restriction of H onto this particular X, right? That's all. So I'm not even saying that the VC dimension is equal to log of the size of H, right? So all I'm saying is that the VC dimension is at most log of the size of H. It's an upper bound irrespective of what X is. X could be finite or X could be infinite. But no matter what happens, it can't be, all this is saying is that it can't be any larger than log of the size of H. That's it. It could be much, much smaller. It could even be 0. Can you repeat? Yes. Okay.
Then the cardinality of X is
Yeah. Cardinality of HXM, not necessarily, right? Okay, because log of the size of H need not be an integer. H, if the size of H is 2 to the power some integer, then that's a different story. Cardinality of HXM, cardinality of HXD is 2 to the power D, yes. No, right? So, for example, D need not be equal to log of the size of H. That's the point, right? Let's just take. You just restrict your class of alphas. Suppose alpha can be 0, 1, or 2. Let's say 3 different values of alpha. What is the size of H? 3. What is the VC dimension? Or let's take 4 different values of alpha. That doesn't matter. Let's take 4 different values of alpha. The VC dimension is at most 1. But the size of H is 4. So VC dimension is less than log of the size, the cardinality of H. Okay. So again, we've seen what the VC dimension is, and ultimately our interest is in connecting this to pack learnability, right? So what is the exact connection? So the problem of binary classification is rather special, because as it turns out, many properties turn out to be necessary and sufficient for pack learnability in the case of binary classification. In fact, we have a bunch of different equivalent conditions for a binary classification problem to be pack learnable. Right? So again, we fix a domain X. The label set is 0, 1. And the loss is the 0, 1 loss. That's the assumption. So we're doing binary classification. Then for any hypothesis class H, the following properties are all equivalent. The first is that H has the uniform convergence property. Which basically says that as long as you have a certain number of samples, all empirical risks are going to be very close to the actual generalization errors. The second is that any ERM rule is a good agnostic pack learner. So when I say any ERM rule, it means that when you do empirical risk minimization, there could be ties, right? There could be multiple minimizers of the empirical risk, and then you have a fixed rule as to how you are going to break these ties. How do you choose which empirical risk minimizer you will select, right? H is agnostic pack learnable. As I said, by any ERM, when I run empirical risk minimization, there could be multiple solutions to the empirical risk minimization, right? And you fix a rule to decide which one you're going to pick. The empirical risk is the same for all the minimizers, and you decide how you are going to pick one of them. But no matter what happens, you will always select the one that minimizes the empirical risk.
Like arbitrary and not just.
Yes. What do you mean, not random?
Like an arbitrary.
Okay.
So it means that no matter like what it shows.
Sure.
But
Yes.
sometimes when you say like it's true for any random x, so it means that when you randomly pick x,
Sure.
then by randomly as in like when you just pick x at random, as in like I mean there's this probability aspect.
I understand. Throughout, we're assuming that the learning algorithm is deterministic, right? So So when I say any ERM, that's why you decide a rule, a deterministic rule as to which minimizer you will pick. Okay. Now, some of these things can be extended to randomized learning algorithms as well, but for now we're not going to take any such complicated situations. Right? So the third point says that H is agnostic pack learner. Again, remember that what I'm saying is that all of these are equivalent. So in the case of the special case of binary classification, at least from the first 3 points, what it means is that if H is agnostic pack learnable, then empirical risk minimization is good. It is going to help you achieve small epsilon delta error. So you don't need to look beyond empirical risk minimization for binary classification. In fact, so if it is agnostic pack learnable, obviously it is also pack learnable. But in general, the reverse is not true. But again, in the case of binary classification, if it is pack learnable, then it's also agnostic pack learnable.
That is only if H is equal to 0.
If
H is equal
exactly, yeah.
to or the equivalent. What if my H
It's
is
only for binary classification, right? So obviously, if it is agnostic pack learnable, then it is pack learnable. Any problem, right? Because here you're looking at all possible joint distributions. But in this case, it's a very specific case where the functional relationship between X and Y comes from H. Right? So this is a very restrictive case compared to this. But somehow, magically, in the case of binary classification, it turns out that if it is pack learnable, then it is also agnostic pack learnable, which is surprising. Yeah, so H is, let's assume that H is equal to C.
H function of C can be agnostic.
Correct. Yeah,
It can be, right?
yeah, where C is a strict superset of H, you mean. Yeah.
But so that's the case, then H is also pack learnable.
Well, that is clear, right? When I say pack learnable, it means that H is equal to C, right? It's a specific class of ground truths. But agnostic pack learnable means that you're looking at all possible random ground truths, random relationships between X and Y. So obviously, this is a special case of this. But in general, the reverse is not true. If H is pack learnable, in general, H need not be agnostic pack learnable. Okay? But for the case of binary classification, the reverse is true. It doesn't mean that the sample complexity is the same for these two. Okay? Sample complexities could be different. That's fine.
Learnability can be.
As long as the sample complexity is finite, it is learnable. That's it. That's all. That is all that we require. So again, I'm not saying that the sample complexities of these are the same, but there's a direct relationship between the sample complexities. Sample complexity of this is something, then this is related to that. No. So what I'm saying is that when I say that the following are equivalent, it means that if one of these is true for that particular hypothesis class, then it means that everything else is true. So if H satisfies any one of these properties, then it also satisfies the remaining 5 properties. Correct. So if H does not have finite VC dimension, yeah, but that is clear, right? If H does not have finite VC dimension, then directly from the no free lunch theorem, it is not agnostic pack. It is not pack learnable, and therefore not agnostic pack learnable. Right. But what is special about this is that as long as H has finite VC dimension, H could be infinite. But if it has finite VC dimension, then it is pack learnable. And something even stronger, H has the uniform convergence property, which, as we've seen previously, is a sufficient condition for pack learnability. Right? So this we have seen, right, from 1 to 2, we've seen before. And again, by definition, if 2 is true, then 3 is straightforward, because ERM is one specific learning algorithm. And if it is agnostic pack learnable, then H is pack learnable. That is also clear. And if ERM is a good agnostic pack learner, then it's also a good pack learner. That's also straightforward, right? Because pack learning is just a special case of agnostic pack learning. And if it is pack learnable, then it should have finite VC dimension. That is also clear. Because if it has infinite VC dimension, then it is not pack learnable. So this is also clear. So if we are able to show that 6 implies 1, then we are done. Right? It means that all of them are equivalent to each other, just by a circular relationship. Right? So VC dimension is what ties all of these together. Right? Any questions? Okay, so let's stop here.